nice cakes. I was telling it is hard to be in Brazil and say no to dosage age. So the second part of this tutorial, which is shorter, I should be able to finish in 1.5 hours before 5:30, including some discussion, is on the analysis of texture. As I mentioned earlier, first you have pre-processing steps. Filter the given image, make it better, remove noise, improve its quality, contrast, detect regions of interest, segmentation. And that is the pre-processing or the image processing part. Next is the analysis. After you cut the regions of interest that represent what you are trying to analyze, tumor or blood vessels or whatever, then you can subject these parts of the images that you have cut, segmented out, for further analysis. So in my book, chapters 1 to 6 deal with pre-processing, filtering and segmentation detection. Chapter 6 was what you saw earlier, shape analysis. Analysis of texture is quite a big area. I'll show a number of examples and a few methods. You have already seen some of them in the presentations given by Dr. Leticia and in my presentation this morning. So there will be some repetition, but I'll give you some more methods and examples. So this material, the format is different. I have cut parts from chapters 7 and 8 of my book. You may see some numbers. Those numbers are related to my book, but I will not be able to do all of that material. To do all of chapter 7 and 8 will require at least 2-3 days. So this is a summary. If you are interested, again, please go to my website. You can get this and also the full notes for chapter 7 and 8. So what is texture? In the context of medical images, we are talking about medical images, so I can give you some examples. But in general, texture is the pattern, these stripes on my shirt. That's the feeling of the cloth, or the patterns, either the feeling of the wooden floor, or the pattern, visual texture or tactile texture. So this is smooth touch, and this may be a little more rough. It has some texture, some grains of the wood. That is texture. The texture in that concrete wall, that is random. The texture here is oriented. There is a certain pattern in the wood grain that is oriented along the length of the tree, the height of the tree. So there are different types of texture in real life. In medical images, texture is affected or created by different phenomena. Some may be intrinsic, some may relate to or be affected by the mode of investigation. Is it ultrasound, is it X-ray, is it magnetic resonance imaging? The texture will be different. So here we have a part of a liver. These are all computed tomography, X-ray computed tomography images, two-dimensional slices and very small parts. This is part of the liver. This is texture. What kind of texture is it? Maybe random texture. This is a kidney, slice of a kidney. What is this? Random texture. This is a slice of the vertebra. You can see the edges of the bone. That's not texture. Inside, there is some variation in gray level. That is texture. Sorry. This is fairly smooth. So maybe there is not much texture. As compared to this, this is quite rough. If you were to convert this to tactile sensation, this is rough, like granite. This is smoother, this is very smooth. But we are talking about visual texture in terms of variation of gray level, intensity, here, X-ray attenuation converted to Hounsfield units. Here, part of the lungs, the airway tree, branching. It's coming here, branching, branching again. So this is the airway tree, a small part of it in the lung. Is that texture? Well, maybe. It is not random texture. There is order. So, and there is orientation. So this is oriented texture. But it is not oriented like the grains of wood. So this is fractal texture. Iterative branching pattern from the main airway branching and branching again and again. So there is a repeated branching pattern. So it is like a fractal. Fractals can also be classified as texture. If you look at only mammograms, because we have worked with mammograms quite a bit, here are some examples. This part of a mammogram, very cloudy, you don't see any structure. So this is like random texture. Here you see some oriented patterns and some random texture. Here you see some oriented fibroglandular tissue. Here you see some oriented tissue and also some cloudy patterns. So in a mammogram you can expect random texture and oriented texture. So there are many types of texture and you cannot analyze all of them using the same technique. You need many different approaches to texture analysis. And some more examples. This is an image of endothelial cells in the cornea. So these are almost hexagonal patterns, like a beehive. So what kind of a texture is that? It is ordered or regular or almost periodic texture. The same kind of pattern repeats. But this is not equal to that. They're not the same. They're not perfect hexagons, but almost hexagon. This is an image of a fly's eye. Compound eye, not mine, but of a fly. And each one of them is a sensor. And there is a repeated arrangement of these. So it is called a compound eye. What is that? It is also ordered. Is it periodic? Almost. So instead of calling them periodic texture, they are referred to as ordered texture. There is some order in the placement of the same unit, which is repeated. So these two are ordered texture, almost periodic. This is the belly of a cobra, of a snake. So you see these elements repeated. You see those elements repeated. They are different. When a pattern is repeated, it is periodic texture. This line is being repeated. So this is periodic texture. So this is a texture unit, or sometimes it is called a texton. This is repeated. This, it's the projection, the curvature of the belly of the snake. So maybe these are all the same, but with the curvature, the image is distorted. So this is also periodic texture. So there are many biological entities naturally exhibiting regular periodic texture or random texture in medical images, depending on how the images were obtained. There is an interesting analogy. In the synthesis of texture or generation of texture, the analogy is made between the generation of texture and generation of speech. Those of you who have done speech analysis can recognize this model. In human speech, we have some major types of speech or phonemes that we generate. Vowels, a, e, u, These are repetitive, these are periodic, there is a pitch, and there is a fundamental pattern. The same pattern repeats. The pattern is different for A and E. The same A, I can say A. The pitch is different. But the pattern remains the same in one-dimensional signal. And then there are fricatives, S or J, S, F, and J. These are fricatives. When you say A, your vocal cord vibrates, and the air that is coming from the lung is chopped into pulses. So when you say ah, you can feel this glottis vibrating, and it is opening and closing, and there are puffs of air coming into the vocal tract from here up to the end of the lips and through the nose. This is the vocal tract, including the oral and the nasal parts. When you say ah, you are putting puffs of air, little pulses of air. But the shape of the pulse here is like an impulse. When it comes here, depending on the shape of the mouth, it is filtered. It takes different shapes. So the sound is different. Ah, E, oo. The input here is the same, but the output is different because it is filtered by the vocal tract. So this is the model for basic speech generation in the human vocal system. When you say is, s, or f, there is no vibration here. You are pushing random noise through, and the vocal cords are not vibrating, but the random noise is filtered, so the output is not white noise, it is filtered noise. So s is different from f. And then there are plosives, h, t. So you close the vocal tract and then put a little explosion, h. So that's different, it's not in this model. Here, the input can be random excitation if it is unvoiced. The vocal tract is activated by random input. If it is voiced speech like a vowel, the input is quasi-periodic pulse because the vocal cords are vibrating. Ah. The vocal tract filter depends on the shape. Ah, E, oo. So the shape is different. You can generate different types of speech. There is a parallel here for texture. The texture element or texton is also referred to as the spot filter. It is an image, it's a little picture. What is a picture like? It's this, or this, or this. That is one unit, sorry. And the input is a random field or ordered field, impulses. But the impulses are now in 2 dimensions. So you can get this by convolving a filter response like this with impulses here. For every impulse, this is copied. And then this and impulses here, 1, 2, 3, 4, 5, 6. And for this, one impulse at every position. But these are not exactly the same. So the model is only approximate. You have to build some randomness in the repetition. The texture unit is distorted from one repetition to another, slightly. So if you allow for that, these 2 models can be compared. One is random noise input, the other is ordered impulse train, impulse field. So here is a random field, random numbers generated. This is the Fourier spectrum, almost constant, white noise. Oh, I shouldn't touch this button. Sorry. So this is a random field in the image domain. This is the Fourier transform. So this is random texture. This is its Fourier transform. When you use this as a textured element, the Fourier transform of a circle is a Bessel function. This is a different circle, bigger circle, more low frequency and reduced high frequency. So these are textured elements, these are their Fourier transforms. When the random signal is given as input to a linear shifting variant system with this impulse response, the input spectrum is this. The input spectrum gets multiplied by this spectrum, and the output spectrum is this. The output texture is this. So this is texture generated by this pattern using a random input field. Excitation is random. So you get random texture. If you use this, you get this similar, but this is smoother, bigger blobs. The Fourier transform. Now the Fourier transform of the input is almost constant. So the Fourier transform of the output for this input is this, and almost the same. The Fourier transform of this input and the corresponding output, almost the same. So if the input is random, the output spectrum shows the characteristics of the system, the textron. I'll show you ordered structure later, ordered texture later. Let me just check. Yeah, okay. Fractals have a few different definitions. The most common definition and imagination of a fractal is self-similarity at multiple scales. So this is a fern leaf that I picked from my garden, scanned it. So this is the pattern. And if you take one part, this is similar to this whole pattern. And if you take this one piece, it is similar to the whole. But it is a physical system, it is a plant. So this is not differentiated so much, but it looks similar. There are only 3 scales here. In most physical systems, the size of the material used or the resolution that you can achieve in imaging will limit the number of scales of repetition. But you can see 3 scales. 1 scale, 2, 3. After that it is lost. So such repetition, self-similar patterns at multiple scales is a fraction. And then you have cauliflower, broccoli. They all have similar structure. You take one piece of broccoli and zoom, it looks like a big broccoli. Take a little piece of that, zoom, it's the same thing. So even if you eat a little piece of broccoli, it's like eating the whole thing. And there is another type of fractal. I mentioned the lung airway tree, artery branching tree. They're all branching patterns. There is a rule to generate this repeated branching at multiple scales. And then there is another model based on, this is not fractal, it should be fractional Brownian motion, a random walk. So this is texture generated by this 1/f model. It is called 1/f model because the spectrum, the power spectrum, decays as a power of 1/f. It is called 1/f to the power of beta. Here beta is 1. In such a model, you get a random signal, 1D, 2D, multi-dimensional. So here, depending on the fractal dimension, there are 2 images generated. They look like mammograms or clouds. Mammograms sometimes look like clouds. Clouds sometimes look like mammograms. So sometimes we have fun looking at a cloud and say, look at that, it's like a craniocaudal mammogram and there is a spiculated tumor. And children would talk about something else, animals I suppose, and if you work with cancer too long, you talk about other things. So here the fractal dimension is 2.3, this is 2.7. Higher fractal dimension means more roughness. This was synthesized. So how do you analyze all of these patterns? They are very different. So you need multiple approaches. There are statistical approaches and then there are structural approaches. The statistical analysis of texture is based mainly on the statistics of gray level, the intensity or density or pixel value. You have already seen this. I'll quickly mention some basic definitions. When you have a probability of gray levels PL, L is the gray level, 0 to capital L minus 1, PL is the probability density function. It is the histogram of the image normalized or averaged over many images. The kth central moment is defined as L minus the mean, μf, to the power of k. So this is the central moment with respect to the mean of order k. The mean is the first moment without the central, LPL. So that is the mean, no problem. Variance, L minus mu square PL, and skewness M3 divided by M2 to the power of 3 over 2, kurtosis M4 divided by M2 square. So these are known statistics of the histogram. Now some people call this first order histogram, but strictly you should call it zeroth order histogram. If you consider how many neighbors of a pixel are you considering? Here you are only considering one pixel at a time, not more than one. So 0 neighbors. So you can call this zeroth order histogram, but the order of the statistics here could be called second order. So there is room for a little bit of confusion as to what is the order of this moment. What is the order of this probability density function and what is the order of the moment. I'll get to that later on. And then there is the gray level co-occurrence matrix. We have seen this before. This is my own picture, my right eye, and this is the set of values in this image. This image is 16 pixels by 16 pixels. The original image had 256 gray levels, 8 bits per pixel. Here I reduced to 3 bits per pixel. So the values are 0, 1, 2, up to 7. So this is an actual image. So as you saw yesterday, gray level co-occurrence is based on 2 pixels, the probability of 2 pixels occurring side by side. This is the probability of 1 pixel on its own, anywhere in the image. Now here we are asking 2 pixels, so there can be 1 with 1, 1 with 0, 0 with 1, 1 with 2, 2 with 1, 2 with 3. So there are 8 times 8, 64 combinations in any one direction. For gray level co-occurrence, we need to specify the direction. Where is the next pixel? If this is the current pixel, is the next one here or here? If this is the current pixel, where is the neighbor? That or that or that or that, which one? You can also jump 2 pixels. So you have to specify a distance and angle as to where is the neighbor, to consider 2 at a time. So then you make up this matrix. Here we define the second pixel is immediately below the first. So this is 2, 5, and this is 5, 6 as a pair. So then, because there are 2 variables, 2 pixel values, and each one can take one of 8 values, there are 64 possibilities. And this is the number of times 00, 03, 04, 01 have occurred in the image. And because this image is of a real entity, my eye, there are no rapid changes. There are some fast changes. There is a white part, and then there is the black part of the eye. I don't have black, I have brown, but it's grayscale. But still, adjacent pixels tend to have similar values. 2, 3. You don't get 2 and then you get 2, 0, but you don't get 7 and 0. You don't get 1 and 6 side by side. Very few. But you get 2 and 2, 4 and 6, 4, 5, 3, 2 side by side more often. So the number of occurrences or the probabilities along the diagonal and near the diagonal will be large, and these will be very small. You normalize this by dividing by the total number of combinations, convert this to probability. These are high probabilities, and 0, 7. There is no 0, 7 in the image. Okay, there is no 7, there is not much 7 there. 5 and 1, 5 and 0, 5 and 1. Not there. 5 and 2, only ones. So this is the gray level co-occurrence for one definition. Then you can define the next pixel is above, to the left, to the right. If it is 3D, behind, above. So you can define for many orientations, or you simply say, I don't care. Current pixel and any of the neighbors immediately connected, give me that. And then Haralick and others defined a number of measures based on probability density functions and moments of probability density functions and some variations on them. And the basic definition is that the gray level co-occurrence matrix PL1, L2 is normalized by dividing by the net sum. So this is now a probability. The sum of all of this set of values will be equal to 1. Then you take various moments. You also define marginal functions, integrate or sum PL1, L2 in the L2 direction, in the L1 direction. You get PXL1, PYL2, X plus Y for K being L1 plus L2, X minus Y, K being L1 minus L2 magnitude. So these are another set of probabilities derived from the original co-occurrence matrix. And then there are a number of values, features. F1, sum of P squared L1, L2, all values. These are all probability values. A very small value will become even smaller when squared. Large value becomes larger. So a homogeneous image will have a large number of, or will have large values for only a small number of entries along the diagonal, which will lead to a large value of F1. An inhomogeneous image will have small values spread over a larger number of these combinations, will give a lower value of F1. And then weighted by K squared, F2, K is L1 minus L2. So if the difference is large and the occurrence probability is large, this will be large. So if it is an image with high contrast, so it's called contrast. And so on. There are many, I won't go through all of them, but these are all moments, L1, L2 times PL1, L2. Like the moments we saw earlier. Moments of probability density function. Now, the order of this, because you are considering two values at a time, you can call it second order or first order. There is some confusion in the literature about that. Central moment, L1 is like a variance. And here, the difference is divided. So it is inverse difference moment. And this is average, K times the probability. And this is another moment, some variance. And there are a few measures of entropy. P log P. Some probabilities, log of that probability. Summed over all occurrences of that, minus. So when a probability density function is uniform, all events are equally likely. And that is supposed to give a high amount of information. When the probability of one event is equal to 1, everything else is 0, then you know what is happening. So there is no information conveyed by such an event. So when all the events are equally likely, when the histogram is flat, this will be maximum. When there is structure, the value changes. So another entropy, P L1, L2 log P L1, L2, summed over all L1, L2. So like this, they define a number of values, number of features, 14 of them. And they have been used in many medical applications of image processing. We have also used them in comparison or for comparison with our features, and also in combination with the features that we have developed, as I showed this morning with the mammography example. So here is an example of a mass in a mammogram. And when you want to analyze masses, this is a benign case. I don't have a malignant in here. Okay, this is a benign one, fairly smooth boundary and well circumscribed, sharp boundary. The contour drawn by the radiologist is shown here in black line. Now you want to calculate the texture measure for this. What should be the region to use? Should I use this whole region? This region includes the background. The tumor or mass is only this much. Why should I include all of this? Who drew the boundary? Why was the boundary not only this much or that much? So these questions are difficult to answer. Which part of the mass is important for texture analysis? So in discussion with the radiologist, what we determined is the core of the tumor here has no useful information. The important information to discriminate between benign masses and malignant tumors exists in the periphery. How is the mass interacting with the neighboring tissue? Is it a sharp transition or is it a blurry transition? So for that we said the region to be used to compute texture should not be the whole mass, should not be a rectangle or square, because it contains all this other stuff. Instead, if you can get the boundary, either drawn manually or detected automatically, we said let us make a ribbon around it, a little bit to the inside and a little bit to the outside. How much? You have to determine based on the resolution and the application. This can be obtained by morphological dilation and erosion. So this ribbon will eliminate the core of the tumor, will eliminate the background outside the tumor, but the shape is related to the shape of the mass. Now use these pixels and compute whatever you want to compute, and then the measure is specific to the mass. The background will not have influence, the core will not have influence. So using the boundary, we also drew perpendiculars, normals to be contoured at every pixel. And we computed the gradient. So gradient is typically computed as this minus adjacent horizontal and vertical differences. But here we said that's not the way we should compute. We should go in a direction perpendicular to the boundary of the contour. And we show that these measures are useful in discriminating between benign and malignant examples. I won't go through the results, I'm just showing the methodology. Sahil and others proposed a transformation. We did not transform the ribbon, we just left it the way it is in the image and computed statistical measures, including texture. Sahil said, if this is the tumor, take so much of the ribbon inside the tumor and take that and stretch it, make it a rectangle by geometric transformation. So this is a tumor, this is the segmented region. They took the ribbon and made it straight, rectangle. So when there is a spicule here like this, you will see a line here. And they did texture analysis using this. Essentially, similar to what we are doing in that a ribbon is used. How the ribbon is defined and how it is used are a little different. So this is in the image domain. We are using pixel values directly to compute statistics. Or you can also analyze in the Fourier domain. You can take the Fourier transform and look for certain patterns that can be related to texture. So you take the Fourier transform, but instead of working in Cartesian coordinates or rectangular coordinates, UV, the Fourier transform is FUV, we said let us convert to polar coordinates. R is square root of u square plus v square, t or theta is arctangent of b over u, we get FRT. And then we can get FR as integral of the theta direction, FT as integral in the R direction. We can convert the two-dimensional Fourier transform into two functions, one for radial frequency, one for angle. Now we can separate the analysis into radial frequency and angle. How does the texture vary with angle? So here's an example of periodic texture. So here we have an impulse field. All these dots are impulses, uniformly arranged. That is the input to the system. The block diagram I showed earlier. The system response is this, a circle. So when it is filtered, when this input is filtered by this system, you get this texture. The circle is placed at every impulse. This is ordered texture. I showed random texture earlier for the same texture element. So this is ordered texture using the same spot noise model, whereas previously we had random texture. Same input. But the input here was random, which gave random texture for this system, texture element. Now, for the same input, same system, texture element, the input is not random, it is structured. And the output is periodic texture. This is very basic model, but the illustration conveys the idea. Now in the frequency domain, it's more interesting. The Fourier transform of a periodic impulse train is another periodic impulse train. The separation between the impulses in the frequency domain is the inverse of the period in the time domain. In 2 dimensions, the Fourier transform of this is this. Another impulse train, impulse field. The separation between the impulses is inverse of this separation. When you put this through this filter, you get the 2 of them convolved in the image domain. In the frequency domain, these 2 get multiplied, and the Fourier transform of the output is this, which has a number of these bright spots. And Leticia showed some examples like this before. So when you see bright spots like this, that indicates the presence of periodicity of some kind in the image. So when you take the Fourier transform and display and there are some bright spots, the separation between those bright spots will give you the pitch or the periodicity of the pattern in the image domain. How do you detect that? Well, you have to detect peaks and so on. We'll not worry about that. You can convert that to polar coordinates. It's an interesting, pretty image. I don't know if it helps. So here, although it is polar, I'm plotting on a rectangular grid because the display is like that. But this is radius and this is angle 0 to 180 degrees. Periodicity, all those impulses are showing here. And you can get FR and FT. This is FR, this is FT. The distributions in radial frequency and angle. This separates the spectrum now. Increasing frequency with radius here. And as you go around the image, how does the spectrum vary with angle? This may not be useful now, but we will see later. So here is the Fourier transform of the fly's eye. You see these bright spots. The fly's eye is, I'll show that picture. I should have repeated it here, but I didn't. This one. The Fourier transform of this image is here. So these bright spots indicate the presence of periodicity, and by measuring the distances between them in the horizontal and vertical directions, you can get the periodicity. If you convert to polar coordinates, you get this. I'm not sure if this is useful. This is FR and FT. Again, how you analyze this depends upon the application, but we can analyze them more easily in this one-dimensional version than in 2D perhaps. Or you can do the equivalent operation in 2D. So these are some examples of texture and analysis using the Fourier transform and co-occurrence matrix. This morning I already showed you application to the case of architectural distortion. I'll just briefly repeat it here. This is a region with architectural distortion. We expect a broad distribution of angular power. The Fourier transform in the Cartesian system doesn't show that. When you convert to the angle and radial frequency, still I cannot see that. But when I convert to the radial distance spectrum and the angle part, and display the angle this way, 0 to 180 degrees, it's very easy to see. There is a broad distribution of power over angle. And here, taking the radial frequency in one dimension, there's only one frequency here, and plotting log spectrum versus log frequency, if there is a straight line portion, that indicates this image has fractal property. Fractal based on the fractional Brownian motion, 1 over f model. 1 over f is this spectrum reducing with frequency. The slope of this line is related to fractal dimension, 8 minus slope divided by 2. You can get the fractal dimension of this image. So we use that in the analysis of architectural distortion. I won't go through the result here, that's not important. But the results are important, but not now. So here is an example of a false positive case. Some structures intersecting. The angular distribution is narrow, some here, some there, nothing in between. The slope is different, the fractal dimension is different. What is important is they are different, the number doesn't matter. So to get to this result, we are using the Fourier transform and conversion to radial or polar coordinates. I mentioned loss convolution operators or loss texture measures. Analytics measures are based on statistics. So it is statistical analysis. The frequency domain method I showed just now is based on the Fourier transform. So that is spectral analysis. Loss took a different approach and said, we want to analyze structure. What is the structure that is present in the image? So statistical, spectral, structural analysis. For this, Loss proposed filters. He started with one-dimensional filters. 1, 2, 1. The output is a combination of the current value plus the previous plus the next. So this is averaging, center-weighted average. You see the average intensity. This is the current pixel minus the previous pixel next to plus the next pixel. This is the difference. Detects edges horizontally. If you want vertical, just do it this way. Spot detection, 2 current pixel minus previous minus next. So these are the basic filters Loss proposed using 3 values in a one-dimensional filter. And then he said, combine them. You can combine 2 of them in the same direction, convolve L3, convolve with L3, it becomes size of 5. 3 samples convolved with 3 samples will give you 3 plus 3 minus 1, 5. It's a bigger filter. So this is local average, this is edge, spot. And then he said this is S3, S3, minus S3 times S3, minus E3 convolved with S3. These, he said, are for ripples and waves. So you are detecting patterns in the image, not tumors and not blood vessels and so on, but generic patterns, edge, spot, ripple, wave. These are the basic patterns that Loss said we should look for in images. And then to convert this to 2 dimensions, you combine them. L5, L5. So L5 transpose L5. So take this, transpose, multiply with this, you get a 5 by 5 matrix. So these are all 5 by 5 matrices. And they can detect edge, spot, ripple, wave. So the example here is the familiar LENA image, and this is just local intensity averaging, detection of the edges, spots. You can't see much here, but when you average and square the values, you get the spot detection and edge detection, spot, wave, and ripple. Wherever the value is large, it means in the original image there is a pattern of this kind. So you take the energy in the outputs of the filters and use them as features in pattern classification. So you add all these values or in a neighborhood of the region of interest. So these are some techniques for the analysis of texture: random, periodic, fractal. Now there is another part to this story which is oriented texture. I mentioned oriented patterns in mammograms, oriented patterns in wood grain, oriented patterns in hair, and so on. So when you want to analyze oriented patterns, you want to detect the presence of objects at a certain angle. And for that you can use a sector angle or sector filter or a fan filter in the Fourier domain. This is the frequency domain: horizontal frequency, vertical frequency. When there is a line in the image at this angle, the Fourier transform will have concentrated energy in this angle, 90 degrees to that image domain angle. So if you put a fan filter past these components and reject everything, you will get components only oriented at this angle in the image domain. Now, this is an ideal filter if you just make it like a triangle. Ideal filters give you ripple artifacts. So you have to make it smooth, so you remove the DC and put a weight here, increasing and decreasing. And also you put a cosine filter so the taper is not abrupt, it is smooth. So we combined and designed this filter and applied to a test pattern. This is the test pattern. We created this test pattern. We made these lines big, thick, strong, just to make it more difficult. This is the Fourier transform. These horizontal lines have the power here. The vertical lines have their power here. The lines at 135 degrees have their power here. The lines at 45 degrees have the power here. So when there are oriented patterns in the image domain, the concentration of power in the frequency domain is related in angle at 90 degrees to the angle in the image domain. So when we apply a filter, the sector filter, to extract only 45 degree components, we get this. All of the others are removed. Only these. There are some artifacts. So you have to put a threshold and detect and make your measurements. What do we want to measure? We wanted to measure the area. For the vertical, this is the output. For 135 degrees, the method failed a little bit here because of substantial overlap. There is so much overlap. What is the direction there? It's difficult. So the method did not work well here. We also designed an iterative method in the image domain, where you apply the equivalent fan filter in the image domain repeatedly. So this is the original image, and this is after one pass, and this is after 9 passes through the same filter repeatedly. Now you see only the vertical components, other components have been removed. And you threshold this and analyze to do whatever you want to do next. So we can perform oriented filtering or directional filtering using fan filters or sector filters in the image domain or in the frequency domain. Gabor filters are the best for this purpose. Gabor filters have been shown to be the optimal to give optimal resolution in the image domain and in the frequency domain. When you make an object smaller and smaller in the image domain, the Fourier spectrum becomes bigger and bigger. As the object becomes small, high frequency power increases. So the object becoming small, the spectrum will become big. When the object becomes very big, bigger and bigger, the spectrum will become smaller and smaller. In the limit, when the object is infinite, constant, the spectrum is only 1 point. So, how do you strike a balance between these two opposite things that happen in the image domain versus frequency domain? Gabor proposed filters that are here. Designed in this manner, there is a Gaussian function in x and y. There are various formulations. I showed one formulation in the morning. This is slightly different. X divided by lambda square plus y square and sigma square. So sigma is the width. X divided by lambda will adjust the scale between x and y. And sigma square here. If you want, you can separate sigma x, sigma y from the 2 directions. So you take this as the basic function and rotate it. Rotate it to any angle you want. And x prime, y prime is a rotated coordinate system with the angle phi. And you can generate multiple filters. So this is the filter in the image domain. As I said this morning, main lobe positive, negative side lobe, positive, negative again, on both sides, on all sides. So this is a mesh plot. This is the Fourier transform. This is an image domain representation. Intensity, the main lobe positive, negative side lobes. There are positive, negative side lobes, but they are decaying, so you can't see. In the frequency domain, as you adjust the scale and orientation, each Gabor filter gives you one Gaussian function which you can threshold to be like an ellipse. This is the region that is passed by the filter. If you change the scale, you go to lower frequencies. So you can specify multiple Gabor filters to take multiple parts of the spectrum. And each one will pass components at that angle only. And for real images, there must be conjugate symmetry, so this must be repeated on the other side. So here, we have Gabor filters for this, for multiple scales. Different scales will pass different thickness. Small thickness, large thickness, very thick. So you have to combine them all, and when you combine, you get all of these components passed. With different gain, you need to threshold and post-process to detect. So this is Gabor filtering at 3 different scales of the same input image. When you combine all of these, you get one output. So with Gabor filters, you can include multi-scale filtering. You can call it wavelet filtering, but simply Gabor functions. So multi-scale analysis, you can formulate in a slightly different way and say x squared divided by sigma x squared, y squared divided by sigma y squared. And j2 pi wx is modulation, sinusoid. This is normalization. This is the Gaussian. This is modulation with the sinusoid. And then you can take this and scale and rotate, and you can form a wavelet bank if you want. So this is scaling. The scale factor is shown here and here. Rotation is here. Or you can do like what I explained this morning. Sigma square x, sigma square y, 2 pi fx. Define the thickness of the object in the image domain. How thick is the average blood vessel or ligament you want to detect? Tau, sorry. Tau, so many millimeters. Elongation, what is the ratio of x to y before the angle changes? Orientation theta, how many filters do you want? F is 1 over tau, sigma x is tau divided by a scale factor. Sigma y is L times sigma x. We believe this is an easier design, more intuitive, easier to design and apply and adapt to various applications because of this factor tau. The frequency F is related to tau also. So this is a set of Gabor impulse responses, filter functions in the space domain. Some reference function, increase L, increase tau, change in angle. These are all frequency responses of these filters. Horizontal frequency, vertical frequency, zero frequency in the middle. Each of these is a Gaussian. This is the Gaussian. So you can filter different parts of the image out, and you can design a bank of filters. This is the two-dimensional frequency space, showing only the upper half. The bottom half is the same thing, reflected. So for each angle, there is a filter. This is the region over which the gain is more than half. And by specifying the parameters, you can place them like this. You can change the arrangement as you wish. As you change the scale, this is high frequency, medium frequency, low frequency, multiple scales. So here we have 4 scales, 1, 2, 3, 4, 12 angles, angle bands. We apply 100 to 80, not 12 bands, to mammograms. And then what? We get 180 output images. And we don't want all those output images. We want only one magnitude image response. So we say for each pixel, take the maximum of all the 180 values over the 180 Gabor filters. So this now has all oriented patterns detected at all angles. Anything that has no orientation is removed. Anything that does not match the scale of the filter is removed. So we are detecting fibroglandular tissue in a certain range of thickness, and we are ignoring other details in the image. Intensity is removed. And then we get the angle field, which indicates the angle of the filter that gave the maximum response of that pixel. So this gives the dominant orientation of the tissue pattern at that pixel. So we can detect oriented objects and get their angle in one step. We use the same method to detect blood vessels in retinal fundus images.
Raj, may I ask a question? Because in this image where you take the maximum value in all the responses, all the filters, it means probably some pixels you have more than one orientation. It responded for several filters, because probably you could have 2 different orientations crossing that pixel. So that means when you take the maximum value, if there's a mirror orientation, but it wasn't that strong, there's another one stronger, you're taking only the strongest one.
Correct. At one pixel, there could be multiple orientations.
Yeah, but if you sum up, you can come up with stronger points would be where you have more than one orientation. And
it is possible. So we have another measure that analyzes the distribution of power at all angles, not simply maximum. We call it coherence. And then depending on that, you can make another decision. But this one is just showing the maximum. So when you come here, the maximum orientation is this. When you come there, it could be 3 things here. This, and that. Which is the maximum? I don't know. But one of them will be the maximum. If you get the same value at 2 angles, what do you do? That's another question. But unlikely, in a real image with real values, will they be exactly equal? Maybe not. But your question is valid. Look here, at this pixel, there are 3 structures at different angles, and they are intersecting. At the point of intersection, we don't know. We have to pick one of them. Whichever is the strongest. Maybe this one is stronger than the other 2.
Anyway, you don't lose any of that because you are taking all of it.
At every pixel.
Yes,
there are lots of pixels. So if there is something that is only 1 pixel in size, it is noise, so we don't care. It must be several pixels long. So if there is ambiguity here, then the others will clarify. So we get the angle at every pixel, but I'm showing this only for every 5 or 10 pixels, or just for display. We can use this information to detect architectural distortion, as I showed this morning. We have also used this Gabor filter output to analyze asymmetry. I didn't talk about it in the morning because that seminar was strictly on architectural distortion. This work was done by another Brazilian student, Ricardo Ferrari, who came from Dr. Paulo's lab and did a sandwich program with me a few years ago. And he's in São Carlos, right? Federal University of Oscar in São Carlos. So this was his PhD work. We segmented what is called the fibroglandular disc in the mammogram. Find the breast boundary, remove everything outside. Find the pectoral muscle, remove that. And take this part only, which is the actual breast tissue, and apply Gabor filters. Asymmetry is defined in terms of differences in density distribution and also orientation. Here we concentrated on orientation. We also added density variation patterns. This talk is on texture, so I'll talk only about oriented texture. So Gabor angle at every pixel and Gabor magnitude response. The magnitude response and the angle are combined to get what is called a Rose diagram. How much of this is at this angle? How much of all of this is at this angle? So this is called a Rose diagram. I showed this for architectural distortion earlier. There we used 180 angle bands. Here we use only 12. So that's why these are bigger sectors. So if you compare the two, they're different. Can you see the difference here? I don't know. Here you can see better. Very clearly, and this is quantitative, not just telling, oh, there is more this way, but objective. So quantitative, objective analysis, take this minus that and compute statistics, make a decision. Symmetric or not? So we showed that this can help in the detection of asymmetry. If you are interested, if you send me an email, I'll give you my card. I can send you papers on any of the topics that I have mentioned. And many years ago, when I started my work at the University of Calgary, 30 years ago, long time ago, long ago, we started working on ligament images. These are scanning electron microscopy images of ligaments of rabbits. This is unfortunately destructive. The rabbit's ligament is ruptured and then it is allowed to heal, and then the rabbit has to be sacrificed. The ligament is the medial collateral ligament in the knee here, not here, not mine, but rabbit. Take that out and then freeze it, fracture it, and you have to treat it for electron microscopy, plating it with gold and so on. And then you scan in the electron microscope and you get an image like this. In a normal ligament, there are collagen fibers, like in a rope, strands of fiber in a rope. The ligament axis is like this. This is a very small part of a ligament. Collagen fibers, mostly straight. A few here and there going in other directions. In the case of a ruptured ligament where there is scar tissue, new tissue being formed, this is collagen, new collagen material deposited in the healing process, there is no structure. It's just deposited. Structure will return slowly as the healing progresses. But 3 weeks after, let me just check here. I'll get to the time later on. So in scar tissue that is new, there is no order, no oriented texture. Whereas in normal tissue, there is preferred orientation. So we wanted to quantify this. We used the fan filter that I mentioned at the beginning. And this is the output at this angle, 75 to 90 degrees. You don't see these other pieces here after Fourier domain filtering and thresholding. This is the output for 0 to 15 degrees. So these parts are here. So after thresholding, we compute the area, we compute the Rose diagram. As you can see, most of the fibers are in this direction. Very little in other directions. In this case, there's a broader angular distribution, almost uniform. So we computed some statistics. These are images from samples, different rabbits, a number of rabbits, unfortunately. And this is 3 weeks after healing, 6 weeks, 14 weeks. The injury was surgically inflicted. And this is another set, 3 weeks, 6 weeks, 14 weeks. The difference is, on this side, the joint was not immobilized. Here, the joint was immobilized. When there is a fracture, we put a cast and the joint is immobilized. But the question is, in the case of ligament rupture, should the joint be immobilized or not? And if you immobilize, for how long? And how does the structure of the collagen fibers in the ligament change with time as compared to normal? So here, without immobilization, 3 weeks. At 3 weeks, there is no order. 6 weeks, there is not much order, but here, there is good order. 14 weeks, almost the same. So with immobilization, there is a quicker return to order. And this is the average over many images and a few rabbits. 3 weeks. This is without immobilization, with immobilization. Even after 3 weeks of immobilization, there is some structure. And 6 weeks here, no structure. Here, good structure. 14 weeks are almost the same. So you can say, just go home, sleep for 14 weeks. You'll get this anyway. Or if you want to return to work in 3 weeks, do this. So this is quantitative analysis. We can derive numbers. We take, normalize this, get the entropy. This is a probability density function. Variation with angle. We don't care what the angle is, but we want the dispersion. So what is the variance or entropy? And this is entropy. So this is the normal band. There is a large band for normal, 1.5 to 2. And here we have the various time points. 3 weeks after injury, 6 weeks, 14 weeks. 3 weeks without immobilization. 6 weeks, 14 weeks. 3 weeks with immobilization. This is already, the average is already in the normal range, but the deviation is large. 6 weeks, completely in the normal range, 14 weeks. Without immobilization, 6 weeks, it is still outside the normal band. 14 weeks, they're all there. If you immobilize for 6 weeks, put the cast for 6 weeks. So if you rupture a ligament, you will be limping in this cast for 6 weeks. Does that help? 6 weeks. But with immobilization for 3 weeks only, and the cast removed after 3 weeks, 6 weeks, it's the same. So this tells that you do not have to put the animal in a cast for 6 weeks. 3 weeks is enough. And at 6 weeks, they are the same. At 14 weeks, they're all the same. So if you can wait for 14 weeks, you can do whatever you want. If you want to go back to work in 3 weeks, immobilization for 3 weeks is good. So in this way, you can compare different ways of treatment and ask the question, how are these different types of treatment affecting structure of the ligament in terms of the oriented texture of collagen fibers. This is what my colleagues, Dr. Frank and others, had done visually, qualitatively, subjectively, and they knew what was happening. Not that they did not know. But with our collaborative project, we could put numbers and show quantitatively and objectively, this is the core of image processing and pattern recognition that you have heard for 2 days now. So how do you quantify this? So look at this and say, well, yeah, there is some return to order. This is returning faster, but by how much? Can you put a number? Yes. So we call this the healing curve. and you can compare and say which method is the best. And then that can be somehow translated to treatment for human beings. That's not my business, that's what the surgeons and orthopedic specialists do. But this kind of a study helps in establishing what is the baseline for normal and how does structure change in response to injury, in response to treatment. So that concludes this portion of the lecture on texture. I have made it short. I have just pulled some important points from 2 chapters in my book. So if you want, you may download the notes for chapter 7 and 8 from my website. Lots of pages and lots of details. And let me know if you are interested in that. If you have any difficulty, I didn't put my email here. You can, I'll give you my card if you're interested. And if you send me an email, I'll send you the papers or the location of my website. Thank you for your interest. If you have any questions, let me know. We still have some time for discussion. I thought I may go till 6 o'clock, but it's only 5:15. We're not going now. We'll have some discussion, some questions. Thank you. Any questions?
What's your research today in this area?
What's my research today? So mainly on retinal fundus image processing for an application in pediatric ophthalmology. For premature babies, there is a risk of development of a type of retinopathy called retinopathy of prematurity. If it is not detected early and treated, the child could go blind. And for that, we need to analyze the pattern of blood vessels in the retina. That is what we are doing. Next week, my PhD student, Faraz Alomi, is defending his thesis on this topic. So it is also oriented pattern analysis of blood vessels. We have used Gabor filters also to detect blood vessels, but after that the analysis is different. Thickness, parabolic modeling to get the openness of the vessels and tortuosity of the vessels. So that's our main project now. And with Paolo and Ribeirão Preto, we are collaborating on vertebral compression fractures, which he mentioned. And with a few others, I'm still working on a few small problems in mammography. But mammography I have almost stopped. Yes?
There's something I still struggle when dealing with extracting features, texture and shape, and it's regarding to the noise. I feel it's very hard to find a good point on getting rid of the noise. Let's say you're trying to analyze a contour. There's some noise, as you said, and so you don't want all that small detail because it will get in the middle of your analysis or comparison. But if you remove too much, then you lose some of the detail that will exactly lead to a good classification. The same as texture. There are some noise that you don't want, but part of the detail is not noise, it's what you want. So how to, is there any, I don't know, any magic to know exactly how to deal with this?
So this is important. In a practical application, we need to know where is the information and where is noise, or where is irrelevant details. So it is good if we can build this into the filtering procedure and feature extraction procedure. For example, with Gabor filters, for analysis of asymmetry, we use multiple scales. For the analysis of architectural distortion, we use only one scale. We said everything that is very big in the low frequency zone, big in the image domain, is not of interest. Everything outside this very fine detail noise is not of interest. So I want only this at all angles. I don't want that. So by putting that step in the stage of pre-filtering detection, we can remove unwanted detail, thick objects, artifacts, fine detail, noise in the high frequency zone. What should that band be? Depends on the application. In the case of architectural distortion, we are analyzing mammographic parenchymal patterns. And in discussion with Dr. Desatel and looking at the images, we said the average thickness of these fibers that we see, about 200 micrometers. Gabor filters can detect with one scale and with an efficiency of more than 90% approximately, 1/4 of that average times 4 times that. So if I say 200 micrometers, Gabor filters with that parameter can detect from 50 micrometers to 800 micrometers. And that is enough. Anything smaller than that, 50, I don't want. Anything bigger than 800, no, I don't want. So by choosing this parameter, we can reject some of the unwanted details and artifacts. In the case of the contours, for shape analysis, I mentioned you could use parabolic modeling or polygonal modeling, and all the fine details can be removed by fitting a parabola or a straight line in the polygon. In the case of the Fourier descriptors, we are dividing fk divided by k. So we are diminishing the contributions of higher frequency components. Whereas if you increase, multiply by k, you get a noisy result. It is susceptible to noise. So if we can incorporate those considerations, which are very important in the design of the filters, not only for enhancement of the image or pre-processing, but also in the extraction of the features, image domain parts, which are then analyzed for other purposes to detect node or whatever else, then we are preventing the effect of noise and artifacts. But all of them have parameters. And those parameters must be fine-tuned based on the application. Just as you said, when you train a classifier, you have a training set for to determine the optimal parameters. You have another validation set to fine-tune the hyperparameters you call of the classifiers. Then you say, okay, I'm happy with this. Test, the results are good, fine. If not, go back, start again. So this process has been repeated in our studies for various applications. I have not mentioned all of that story, but it is built into all of these steps. Did I answer your question?
Yeah, sure.
I did not read all your papers, but I want to know if you try to use wavelet transforms to extract characteristics from this.
Yeah. So the question was, have you used wavelets? Not explicitly, but this was actually implemented as Gabor wavelet filtering. So as I showed, here, a to the minus m this. So this is a bank of filters obtained by scaling and rotation of this basic function. So if you want, you can consider this to be wavelet, a bank of wavelet filters. What does the bank do? This each filter, this is one scale, 12 angles, another scale, 12 angles, another scale, another scale. So this is the behavior of the bank of wavelet filters in the frequency domain. The Fourier transform is broken into these pieces. So if you want, you can do it in the space domain. If you want, you can do it in the frequency domain. We are not concerned about some scale factors. If you want to call it wavelet filtering, there are these admissibility conditions and scale factors for normalization. We don't care about that here because we are going to put a threshold and extract the components. So if you are willing to throw away those components, you may call this wavelet filtering. if you are particular about those conditions, this is not wavelength filtering we are doing in the frequency domain. So there is a small difference, but essentially the same. Any more questions? Thank you. Good luck with your work. Research.
We want to thank Mr. Rangayyan for the excellent course. It was a little time, but it was a good time. Nós gostaríamos de agradecer a presença aqui de todos os professores que vieram contribuir com o simpósio. Dr. Paulo Monsocini, Dra. Letícia Hitner, Dra. Maísa Mafio. Mais uma vez, nossos agradecimentos. Esperamos que da próxima vez vocês passem mais um dia aqui com a programação turística na cidade, né? Vamos ver se a gente combina isso. O Rangayyan foi mais esperto, vai ficar aqui amanhã, a gente ainda vai dar uma saída. Bom, então, é isso aí. Eu acredito que o seminário foi de bastante proveito para todos nós. Essa área não tem sido muito explorada aqui no estado do Amazonas. Aqui nós só temos alguns eventos na área de telemedicina, vinculados à área de engenharia biomédica, devido à própria natureza do Estado, que precisa dessa ferramenta. Mas, juntamente com o INCOR, com o Marco Antônio, a gente vai ver se inicia essa série de seminários ao longo dos próximos anos, para ver se a gente dinamiza um pouco mais a área de engenharia biomédica aqui na região. Não sei se a professora Marli gostaria de falar alguma coisa. E nós só temos agradecimentos aos nossos convidados e a vocês aqui que estão presentes. Afinal de contas, esse seminário foi organizado em função dos alunos, em função dos professores também que aqui estão. Muito obrigado pela presença de vocês e que os próximos anos sejam melhores, que a gente possa contar com mais pessoas aqui. Vamos ver se a gente divulga melhor o evento. Em hospitais também, em clínicas de radiologia, que eu tenho tido muito proveito vindo aqui, visto essas técnicas, algumas delas muito novas, né, que acredito que ainda não vão demorar alguns anos ainda para estar na prática clínica. Né. E é isso aí, essas são as minhas palavras. Professora Marli.
Informações, né? Está todo mundo perguntando como é que vão ter acesso às apresentações, certo? A gente vai disponibilizar na ferramenta de educação à distância, a gente vai abrir lá um espaço e vai disponibilizar para os participantes. Vocês vão ser comunicados por e-mail, assim como nós mandaremos os certificados também da mesma forma. Tá bom? Obrigada a todos. Boa tarde.
Yeah,